Hey class, it's Mr. H here. We're going to do 8.4, more on vectors. This time it's algebraically defined. If we do it in such a way where we plot a vector on the XY axis and discuss some properties, it actually makes our life easier and as far as adding vectors and other applications. So what we're starting with is called a position vector, and a position vector is such that the initial point is at the origin. So that's the key, right? As in that picture below. Okay. And then its endpoint is at some point AB. Right there. All right. And then it's going to be written with these like triangular type brackets. Right. So if you see that notation, that's a vector. Okay. And the numbers A and B are called the horizontal and vertical components. And then there's an angle, the angle between the x-axis and a position vector is the direction angle. So there's your direction angle right there in this picture. Okay, so one type of problem you'll have to do is, given a vector in that standard position, find the magnitude and the direction angle. And the nice thing about the magnitude, if you think about this, it's a right triangle, and the magnitude is the length of that vector. So really it's just Pythagorean theorem to find the magnitude. And so there's Pythagorean theorem written in a sort of fancy way where the magnitude of the vector has been solved for. And then the direction angle is B over A. The tangent of theta would equal B over A, opposite over adjacent. Right? So you could just use that for finding theta in general. So let's try an example. Here we have, and I've already drawn it out, we have the vector u equal 3, -2. So that means on the x-axis is a distance of 3 and the y-axis is 2, right? So I can even write that in if that helps, right? There's 3 and there's a length of 2. It's negative, right? Going down, that was a weird negative. Let's zoom it in, -2, right? Is the triangle. And so if I want to find the magnitude, I could just plug it right into my formula right here, right? Or you could look at the picture if you want, but it works just like that, right? So A is 3, so we're doing 3 squared, and B is -2. And then if you calculate that, and then just pay attention to what they want. Do they want exact value, rounded, or what? All right, so this is going to be the square root of 13, right? And it said give the magnitude in exact form, so that's exact, right? Don't want to calculate it with a calculator. Okay, and then for the direction angle, notice what I have labeled here. I have a theta prime, right here, that little apostrophe next to it. That's the reference angle. And what I want for my direction angle is this guy, right? So what you're going to do first is just find that reference angle. And when I do that, I'm going to use that formula here, right? And I'm ignoring any negatives. So tangent of the reference angle is opposite 2 over adjacent 3, right? Notice I didn't put -2. I just want the reference angle. That's not going to be the direction angle. It's just the angle inside that triangle, right? And so that means I'm going to just do my calculator tangent inverse of 2/3. Okay. And then approximate that. So if I do tangent inverse of 2/3, make sure we're just going to do these in degrees. All right. So I'm in degree mode and I'm getting 33.7 about. Okay. Now I'm going to use some subtraction or addition or whatever to get that angle, right? So notice that the theta, the positive theta, is going to be 360 degrees minus, so that would be theta, that angle. Right. and there would be my direction angle. So 326.3 is what I get for that. Okay. All right, so a little trickery there to get that angle, right? And away we go. All right, how about another one? Same kind of idea. We got the picture drawn. So let's get the magnitude. Square root of, we got a, which is -3√3 squared plus b squared. Okay, so -3√3 squared, 3 squared is 9, +9, and √3 squared is 3. Right, so I just square each piece there, and then 3 squared is 9. All right. So this is 27 plus 9. Ooh, look at that. That's 36, and that's a perfect square. So my magnitude is 6. For the angle, find that reference angle first. So let's maybe just squeeze it in down here. Tangent theta is b over a. So the b is 3, and the a is 3√3. Ignoring negatives for the reference angle. So I'm going to do tangent inverse of, I guess I can cancel those 3's out. It's just 1 over √3. Okay. And I think that works out to be exactly something, right? That feels unit circle-y. Yeah, that's 30 degrees, but you can do that in your calculator too, right? And then notice, okay, theta is in the second quadrant. So to get theta, since this is 180 right here, I'm going to do 180 minus that reference angle to get my direction angle. So that's 150 degrees for the direction. Okay. All right. So there's kind of step one, or problem type 1 is given a vector, find those two things, magnitude and direction angle. Next, we have little formulas for the horizontal and vertical components of a vector. Going back to just right triangle trigonometry, SOHCAHTOA, right? Just solving for A or solving for B, you get these two little formulas, and they work really well if you need to find the components, right? So here's an example. We have a magnitude 2 and a direction 225. So that's how it would look drawn. Find the components, right? And I put those in the picture as well. So let's find A, and really all you got to do is just stick right to the formula, right? Magnitude of U is 2, and theta is 225. Right? So let's just calculate that. Let's do exact value on this one. That might pop up. Just again, pay attention to the directions, because 225 is on your unit circle. So refer to your unit circle if you don't have that memorized, but the cosine of 225 is -√2 over 2. Sounds familiar, probably, right? And then I can reduce that to -√2. There's my horizontal component. How about the vertical component B? It's similar, just use sine, right? Turns out the sine of 225 is also -√2 over 2. And so B is going to be -√2. There's your vertical component. Okay. All right. We're moving along here. Let's try another one. Here, where we probably don't have exact values, we'll have to use the calculator. You know, on these, you don't even really have to draw them. You just go right to the formula, right? So even though it says find the magnitudes, that's just the same as finding the components, right? So those same formulas, right? My A is going to be 27 cosine 25 degrees, right? And I'm just going to plug that right into my calculator, and it says round to the nearest integer. This is about 25. Right? And then the B is 27 sine 25 degrees. Plugging that in, I'm getting about 11. And those are the magnitudes of the horizontal and vertical components. Just the length of those sides. Okay. Moving along. No reason to stop now. We got this picture. We have this vector W, and it says right in that form AB. Basically, it's the same thing. Find the horizontal and vertical components, and then just plug them into that vector form using those little triangular bracket things, right? But we have the angle and we have the magnitude of W. So my A is going to be 25 cosine 41.7. It says round to the nearest tenth. So 25 cosine 41.7, I'm getting about 18.7. For B, just replace cosine with sine. 25 sine 41.7. These, they work out. Just plug it into the formula. You don't have to worry about reference angles or anything fancy. All right, just calculate it out. And then now we want to write it in that form. So triangular bracket, the A goes first, and then the B. Right, there's the algebraic form of that vector. Okay. So there's two ways you can describe a vector. You can give the angle and the magnitude, or you can give the horizontal and vertical components and put it in that algebraic vector form. Okay. Next, we're going to get into some vector operations. So for vector operations, these are super easy. Okay, you just add, for vector addition, just add the horizontal components together and add the vertical components together, right? This is where the algebraic form of a vector really comes in handy, because notice if you have to like graph it and do it geometrically, you have to, draw your vectors and then draw the diagonal of the parallelogram and then figure out where that ends. It just gets a little messy, but to actually add them, all you're going to be doing is you're going to add the vertical components together, -2 plus 4, and add the horizontal components together, 1 plus 3. Okay, and so this is going to be 2, 4, just like the picture shows. You don't have to draw these though, you just can do it algebraically, right? So we were wondering, why do they call it vector addition when it's the diagonal of a parallelogram? Doesn't seem like you're adding anything. Here's why it's called addition, because you add the horizontal components together, add the vertical components together, and that is the resultant vector. Pretty cool. All right. Also works pretty nicely for scalar multiplication. So if you want to find -2, u was -2, 1. Well, all you do on these is you distribute. So this is going to be +4, -2, right? And notice it as it looks in the illustration, the blue is the u, and then what does it mean to multiply it by a -2? Well, the negative flips the direction around, and the 2 doubles the length, right? Which you get when you do it algebraically. So pretty neat. Okay, and then you can do all sorts of crazy stuff like 3 u's minus 2 v's, and you can draw it out and try to figure it out, but wow, algebraically it works out so much better. I'm doing 3 times -2, 1, which is the u, minus 2 times the v. What's the v again? V is 4, 3. Okay, so let's just write it out like that. And again, just think of it like you're doing algebra. You're going to distribute the 3. So that's going to be -6, 3. And then distribute. Let's distribute that 2 and just change this to a plus. Right, that's going to be a -8, -6. Right, there it is. And picture of it. Right. Okay, and then we're going to add those two vectors together. and I add those together, the two horizontal components added together would be a -14, and the vertical components added together would be a -3. And there would be the end result. And that's what the picture looks like. And we see that's consistent with how the picture is drawn. Okay, let's take a small break there, and then I'll come back and finish this packet in the next video. Hope the section's going okay. We're nearing the end, so hang in there. You're doing great. Send questions my way if you have any. Talk to you later.